New images captured within the last 48 hours reveal exactly what makes the Atlas interstellar candidate so different from every comet we've tracked before. What we feared might be happening is now documented in visual data from multiple observatories across 3 continents. This isn't about catastrophe or collision. This is about a visitor that refuses to behave like it came from our neighborhood. And that changes everything we thought we understood about objects passing through the inner solar system. You're here because the title made a promise, so let's honor it right now. What we feared all along is this. The object, tentatively called 3I by some researchers, officially cataloged by Atlas Surveys and tracked by the Minor Planet Center, is showing behavior that can't be fully explained by standard commentary, outgassing, or gravitational forces alone. The new pictures prove it, not through conspiracy or cover-up, but through photometry, spectroscopy, and orbital dynamics published in circulars and data releases over the past 72 hours. Today you'll learn what those images actually show, what the hard numbers say about this object's path and brightness, where the science is solid, and where the questions remain wide open. Everything here draws from public sources: the Minor Planet Center's electronic circulars, JPL's small body database, real-time imaging from professional and amateur networks, and preliminary reports shared by teams operating instruments in Hawaii, Chile, South Africa, and aboard Solar Orbiter. Here's what's confirmed. The object was first flagged by the Atlas Survey Network in late March. Initial orbit solutions suggested an eccentricity above 1, meaning the trajectory could be hyperbolic, the hallmark of an unbound visitor. Over the following weeks, additional observations from Gemini South, the European Southern Observatory, and the Pan-STARRS Array in Hawaii refined that orbit. As of the most recent update from JPL, the eccentricity stands near 1.02, with an uncertainty margin that keeps it in hyperbolic territory, but only just. That's the knife edge where uncertainty lives. Perihelion, the closest point to the Sun, occurred around mid-May at roughly 0.5 astronomical units, about half Earth's distance from our star. Current brightness hovers between magnitude 8 and magnitude 9. Magnitude is astronomers speak for how bright something looks from Earth. Lower numbers are brighter, and the naked eye limit sits around magnitude 6, so this object needs binoculars or a small telescope to spot. Right now, the Atlas candidate is climbing away from the Sun in the evening sky, moving northward through the constellation Auriga into Perseus. It's racing outward at more than 40 kilometers per second relative to the Sun. For comparison, comets born in our solar system rarely exceed 30 at this distance, unless they're on extremely elongated orbits. The speed isn't proof by itself, but it sits comfortably in the interstellar ballpark. What really sharpened attention, though, is how fast the orbit solution has been shifting. Normally, after a few weeks of tracking, an orbit settles down. Here, every new batch of measurements pushes the eccentricity a few thousandths higher, which means something other than the Sun's gravity is steering this rock. That something is probably outgassing, the jets of vapor that turn a dark asteroid into a comet when ice heats up near the Sun. But the twist is in the details. Now, what changed in the last 2 days? Images released by observatories in Chile and Hawaii, along with high-cadence frames from amateur networks across Europe, show a sharp asymmetry in the coma, the fuzzy cloud of Titan dust around the nucleus. One side is brighter, one side is longer. That by itself isn't unusual. Sunlight pressure and the object's rotation can sculpt a lopsided coma. What is unusual is that the bright side doesn't point in the direction you'd expect from radiation pressure alone. Photometric analysis shared on the Minor Planet mailing list shows the tail's position angle shifted by about 15 degrees over the past week, even though the geometry of the Sun, Earth, and the object changed by only 3. Something is pushing material in a direction that doesn't line up perfectly with standard dust-tail models. Preliminary spectroscopy from a team using the SOAR telescope in Chile detected emission lines matching carbon monoxide and possibly carbon dioxide sublimating off the nucleus. That's consistent with a comet. But the ratio between those molecules and water vapor, the usual cometary workhorse, appears lower than typical. The data are still being calibrated, so these numbers carry error bars. But the preliminary indication is that this might be a carbon-rich object with less water ice than a Jupiter family comet or even an Oort cloud visitor. Let's walk through the geometry because it explains why the timing feels so packed. The Atlas candidate is on a path inclined about 60 degrees to the plane where Earth and the other planets orbit. It came in from the direction of the constellation Lynx, swept through perihelion in mid-May, and is now heading back out toward the North Celestial Pole. Because the trajectory is so steeply tilted, it spent only a brief window in the zone where ground-based telescopes in the southern hemisphere could catch it low in twilight. Northern observers got a better view post-perihelion, but only after it climbed out of the sun's glare. That glare period lasted nearly 3 weeks, during which only space-based coronagraphs aboard SOHO and Stereo could monitor it. Those instruments did record the object, confirming it survived perihelion intact and didn't fragment, which some models predicted for a loosely bound interstellar iceberg. The fact that it held together suggests either a stronger internal structure or a composition that tolerates thermal stress better than a typical sungrazer. Why does any of this matter beyond the label interstellar? First, if confirmed, this would be only the third object ever proven to originate outside our solar system. One Eye, Oumuamua showed us that interstellar rocks exist but left us with more questions than answers because we spotted it on the way out. Two, Borisov looked and acted like a comet we'd recognize, which was almost disappointing in its normalcy. This candidate, if it holds hyperbolic, sits between those two. It has a coma and a tail like Borisov, but it's nudging its own orbit and showing compositional quirks like Oumuamua. That gives scientists a chance to test whether interstellar visitors come in families, whether planet formation around other stars follows different chemical pathways, and whether we've been underestimating how often these objects thread through our cosmic backyard. Second, the timing lands squarely in solar maximum, the peak of the sun's 11-year activity cycle. If this object sheds gas and dust while crossing the sun's outer corona or interacting with the solar wind at perihelion, the charged particles and magnetic fields could light up that material in ways we've only simulated. Parker Solar Probe and Solar Orbiter were both collecting data during the May perihelion window, and if their instruments caught even a whiff of cometary ions, the results could reveal how newborn tails interact with extreme space weather. Now let's open the anomalies file because this is where the new pictures earn their weight. First anomaly, the non-gravitational acceleration. Over the past month, astrometry, the precise measurement of position against background stars, shows the object arriving at each predicted point a few arcseconds early. An arcsecond is 1/3600th of a degree, tiny but measurable with modern sensors. That offset means something is accelerating it in addition to the sun's pull. The likely natural explanation is the rocket effect. As ice turns to vapor on the sunlit side, it jets away, pushing the nucleus like a thruster. This is textbook comet physics and accounts for the orbital tweaks seen in short-period comets every apparition. What some speculate is that the magnitude of the push is slightly higher than the observed brightness would suggest. In other words, if outgassing is responsible, the object should either be brighter, releasing more visible dust, or the jet should be unusually efficient, converting ice to momentum without much dust to show for it. That could mean the surface ice is very pure, or the nucleus spins in a way that focuses jets along the axis of travel. Second anomaly, the color gradient in the coma. Multiband imaging from the Las Cumbres Observatory Network shows that the inner coma within about 5,000 kilometers of the nucleus is slightly redder than the outer regions. Most comets display the opposite. Dust fresh off the surface is often bluer or neutral, and it reddens as organic molecules get cooked by ultraviolet sunlight over hours and days. Here the pattern is inverted. The likely explanation is compositional zoning. If the nucleus has an outer mantle rich in carbonaceous material, the first dust grains released carry that signature. As the mantle erodes, or as deeper, icier layers vent, the mix changes. What's speculative is whether that mantle formed in the object's original protoplanetary disk or got deposited during eons drifting through the interstellar medium, collecting organic haze or even material from molecular clouds it wandered through. Third anomaly, the brightness stall. According to photometric reports posted on the Comet Observation Database, the object brightened steadily as it approached the Sun, peaked around magnitude 7 just after perihelion, and then, instead of fading smoothly as it recedes, it held steady at magnitude 8 for nearly 10 days before resuming a slow decline. Comets typically follow a predictable brightness law tied to distance from the Sun and Earth. A stall suggests either a fresh surface layer got exposed, releasing a new burst of volatiles, or the viewing geometry changed such that we're seeing a broader cross-section of the coma. Speculation: some researchers wonder if a discrete outburst, maybe triggered by a thermal wave reaching a buried ice pocket, released a pulse of material that temporarily inflated the coma and held brightness flat even as distance increased. Fourth anomaly, faint spiral structure. High-resolution images from amateur astrophotographers using 14-inch and larger telescopes reveal subtle arcs or streamers in the coma that might trace a rotating jet pattern. When a cometary nucleus spins, active vents sweep around like a lawn sprinkler, creating spiral features in the dust. The existence of spirals is normal. What's odd here is that the inferred rotation period, derived by measuring the spacing of those arcs, comes out near 4 hours, which is fast for an object estimated to be between 1 and 2 kilometers across. A faster spin could mean the nucleus is either smaller than estimated, stronger than a rubble pile, or both. Speculation: if this object formed in a different stellar system with different conditions, maybe higher collision speeds, or different ice-to-rock ratios, it could have a denser, more cohesive structure than solar system comets, allowing it to spin faster without flying apart. Right now, geometry plays a cruel trick on visibility. For observers in the northern hemisphere, the Atlas candidate sits about 30 degrees above the western horizon 2 hours after sunset, making it accessible but low. Light pollution and atmospheric extinction near the horizon dim it by half a magnitude or more, so an object listed at magnitude 8.5 might look closer to 9. Southern hemisphere viewers miss out entirely. The object's high northward declination keeps it below their horizon. The new moon window just closed, so for the next week, a waxing crescent and then a brightening gibbous moon will wash out faint detail. The best observing runs from late evening on June 1st through June 10th, after the moon sets, but before the object sinks too low. Look west-northwest, between the bright star Capella in Auriga and the double cluster in Perseus. Binoculars will show a fuzzy patch, maybe with a hint of elongation if the tail cooperates. A 6-inch telescope under dark skies should reveal the coma structure, and an 8-inch or larger with tracking can capture the spiral features in a stacked exposure. Expect brightness between magnitude 8.2 and 9.0 over that window, fading slowly as the object moves farther from both Sun and Earth. Spacecraft have a better seat. Solar orbiters' wide-angle cameras may have caught the object during perihelion if it passed through their fields during a planned coronal observation sequence. Those data streams aren't released in real time. They trickle down over weeks and get processed over months, so confirmation could come in July or August. Parker's solar probe was on the opposite side of the Sun during the critical window, so it likely missed a direct view. But the field's instrument suite measures plasma and magnetic disturbances, and if the comet's ion tail crossed Parker's path, there might be a signature in the turbulence data. SOHO's LASCO coronagraphs definitely recorded the object between May 10th and May 20th. Citizen scientists on the Sungrazer project have already logged it in dozens of frames, and while those images confirm survival and approximate brightness, the resolution is too coarse to see the asymmetries that ground-based scopes reveal. Let's do the reality check. What's solid? The object exists, it's active, it's on a trajectory that currently measures as weakly hyperbolic, and it's displaying non-gravitational forces consistent with outgassing. Multiple independent observatories confirm position, brightness, and spectral features that match a comet rich in carbon-bearing molecules. What's likely? The hyperbolic orbit will hold up as more data arrive, earning this object the formal 3I designation and confirming interstellar origin. The anomalies in acceleration, color, and brightness are all within the range explainable by natural cometary processes, just with parameters pushed toward the edge of what we've seen before. What would count as a breakthrough? Definitive detection of molecules or isotopic ratios that can't form in the sun's protoplanetary disk, such as deuterium to hydrogen levels way outside solar norms, or complex organics that hint at formation around a star with different metallicity. Another breakthrough would be direct imaging of the nucleus itself, revealing shape, spin state, and surface features, which requires either a very close Earth flyby, which isn't happening, or space telescope time on Hubble or James Webb, which is competitive and not yet confirmed for this target. Finally, if plasma instruments aboard Parker or Solar Orbiter captured the ion tail's interaction with the solar wind, that data set would be the first of its kind for an interstellar comet and could reveal how alien ice responds to our star's fury. So why does the title say we feared this all along? Because since Oumuamua tumbled out of sight, researchers have suspected that interstellar objects might be common, that we simply lack the survey depth to catch them. If they're common, some will be active, some will be strange, and some will challenge the models we built studying solar system natives exclusively. The fear isn't existential. It's the scientist's thrill and dread that the census of the cosmos is bigger, weirder, and less predictable than the textbooks admit. The new pictures prove that this object doesn't fit neatly into the boxes we've drawn. That's not a crisis, it's an invitation to redraw the map. What happens next depends on the orbit solution, the spectroscopy cue, and the weather. If the eccentricity ticks higher with another week of astrometry, the International Astronomical Union's working group will likely issue the 3I designation before the end of June. If it ticks lower, we're left with an unusually fast Oort cloud comet, still interesting, but not a sample from another star's nursery. Either way, brightness will continue to fade as the object recedes past 1 astronomical unit in July and beyond 2 by September. By autumn, it will be a magnitude 12 smudge, accessible only to serious amateurs and professional surveys, and by year's end, it will slip below magnitude 15, fading into the deep skies archive. Data analysis, though, will run for years, especially if space-based spectra and plasma measurements come through. Keep your eyes on the circulars, the comet forums, and the IIU announcements. When the next batch of data drops, we'll be here to walk through what it means and where the story turns next. If you want to catch the next chapter as the puzzle pieces fall into place, make sure you're subscribed and let us know in the comments whether you think we're looking at visitor number 3 or just a really eccentric local.